So, good morning. I will start the lecture now. I've um, sent an email to some of you because I had made a mistake in the form. And so, about 9 of you will have to respond to that email if you have any difficulty with the changed test date. The test date is now 2nd. This is again changed. 2nd December in class. I'm keeping it in class because I want all of you to be online during the time completely, and also you would have to have your video on like last time. So we will return the test results shortly. Arpita has already graded the tests, and so the test results will be given back to you shortly. I have to go through it once before I give it back to you. So let me start with what I had shared with you in the last class. I think one very important feature is that you should view the three-dimensional structures of these molecules for yourself to see how these factors are really operating in real life. So these two structures I can show to you briefly, and I will post it for you so that you can see it yourself, manipulate it and see it yourself. This is the compound in which the hydride is occupying one position. Okay, this is the position it's occupying, the one I'm highlighting. That's the hydride. It's a rhodium hydride complex. Okay, and it has got 3 triphenyl phosphines. The triphenyl phosphines are in the equatorial plane. Carbon monoxide is in the axial plane. So this is one complex, and the other complex is given here. That's the one where you have 4 triphenyl phosphines and 1 hydride. And you will see that the 4 triphenyl phosphines are almost in a tetrahedral geometry. This is the one that I was talking to you. And the hydrogen is not imposing a full positional, or it's not imposing occupying a full site on a polytope or a polyhedron around the rhodium. So you can see that the angles are 104 degrees and 105 degrees and 113 degrees. Okay, so let me see if you can see that better now. It's 104 degrees and 113 degrees. So you can see that it's very close to the tetrahedral angle of 109 degrees. And it's not perfectly 109, but it is close to it. Okay, so you can manipulate these structures for yourself and see how these structures are working. I'm going to remove them from the screen and go back to this slide where we were. Let's go back to this slide. So let me just refresh your memory. Hydride complexes are what we were discussing in the last class, and I'm going to continue with this, but with a slight variation. We are going to talk about dihydrogen complexes. And the main point that I wanted to drive home was the fact that hydride complexes are indicative of an H- coordinated to a transition metal, whereas the hydride complex could actually be an acid where the hydride, so-called hydride, is coming out as H+. it's actually an acid. So the ambivalent behavior of hydrogen in metal hydrides is something that you have to bear in mind. It will change its behavior, act like a chameleon, changing its color. It will behave differently in different metal complexes. So to understand the nature, you really have to study the chemistry of the complex in order to know whether it is going to behave like a hydride or going to behave like a H plus, H minus or H plus. That question is something that you will know only depending on the solution in which it is present and the environment basically, and the environment within the metal complex itself, the coordination sphere and the environment, the solvent system that you're going to use. So there is a difficulty in assigning oxidation states, because if you consider it as H minus, it's going to have a different oxidation state. H plus will be a different oxidation state. To avoid the confusion, we will uniformly consider a hydrogen as H minus. Okay, that's the way we consider it. I then talked about various methods of making metal hydride complexes. There is some analogy that you can derive to the metal alkyl complexes. So they are analogous. Only difference is you can now add a proton and subtract a proton to make hydride complexes. This is going to continue in the next lecture also. So the structure of the metal hydrides, that's the factor that I just briefly touched upon in the slide. The structure of the metal hydrides and the steric demand of the hydrogen is very flexible. Hydrogen is the smallest ligand that you can think of, definitely the smallest ligand that you can think of, and so it occupies a variety of coordination sites, or it can just be very unassuming and move from one site to another site without difficulty because of its small size and the ability of the ligand to do quantum mechanical tunneling. So these are some complications with hydrogen complexes. Spectroscopically, one can determine the presence of the hydrogen using infrared and NMR. X-ray is a problem. I again emphasize this for you because you have transition metals which have, say, more than 25 electrons around the transition metal and hydrogen having 1 electron. Okay, so you're going to look at a huge peak in the X-ray diffraction from the transition metal and a small blip next to it for the hydrogen. So the ability of the X-ray diffraction technique to detect the hydrogen is very poor, and so one has to resort to neutron diffraction. If one wants to study the crystallographic structure of a metal hydride complex. Now I come to the question of dihydrogen complexes. Now, I already told you that in many complexes, the metal has got more than one hydrogen attached to it. And when you have two hydrogens attached to the metal, so they are dihydride. Suppose you have a dihydridic complex. The two dihydrides can be cis and they can be very close. You don't know whether it is a dihydrogen complex or it is a MH2 complex. So this is the confusion. MH or is it MH2? For a long time, this was discounted. Okay. So in order to, for a long time, this was discounted. I'm putting dotted lines because why? Because this is not really true. Now we have sufficient evidence for the formation of dihydrogen complexes. But it was only in 1983 that a couple of people, primarily this person called Kubas. There are other people also. I will mention their names as I go along. Kubas, for example, found out that there is a very unique system where you can make dihydrogen complex. The paper that he published, in fact, talked about MCO3 cycloheptatriene. Heptatriene, this H stands for heptatriene, so it's a 7-membered ring with 3 double bonds. Now, you can force these 3 double bonds to be flat, and all 3 of them can coordinate to the molybdenum. So that would be this complex. So this complex, in fact, could be like this. I'm exaggerating the bend, this CH2, exaggerating it purely for emphasis. So this is a complex that we're talking about. Remember, just a line in organometallic chemistry stands for a carbonyl ligand. So just like a methyl group, a line in organic chemistry would be a methyl group, a line in organometallic chemistry is a carbonyl group. So here's a carbonyl group, 3 carbonyls and 1 cycloheptatriene. And when it is treated with triphenyl phosphine, there is a displacement reaction. This ligand comes out. Now this is a 5-coordinate system. Remember, this is a neutral molybdenum, molybdenum 0, and so this is now a 16-electron complex. It can accommodate 2 more electrons, and form an 18-electron complex. And it was shown that a variety of small ligands can be accommodated by this molybdenum complex, but in a reversible fashion. Let me see if I can show you that paper quickly. So this is the paper that I'm talking about. That's probably too small for you to read. Yeah, this is the paper that I'm talking about. So what Kubas, this is a paper by Kubas, I think. So what he showed was that this system, molybdenum tricarbonyl system, can interact with a variety of phosphorus ligands. Let me see if I can annotate this. This is going to be tricky. This is okay. No, I will figure this out later. But what I am trying to emphasize is that this figure right here, is the one that I am talking about, where you have molybdenum attached to 2 ligands, and probably instead of this cycloheptatriene, which is what is here, cycloheptatriene is eta 2. They suspected that it is eta 2, and this eta 2 system reversibly interacts with a variety of small ligands, N2, H2, and C2H4. All of them can interact with them in a reversible fashion. If you heat it to 50 degrees, the free form is generated. Okay, I have done something which gives me those dots. So I'll figure this out. Here is the complex that is reversibly interacting with a variety of ligands. Okay, reversibly interacting with a variety of ligands. So this is the paper that he published, and he characterized them using infrared spectroscopy. That's enough for this paper now. I will move this out of the screen so that we'll go back to our presentation. So this is the study that he did. This is the, and dihydrogen was one of the small ligands that could be utilized for coordination. Now, what I thought I would do was to show you the complex in 3D again, the 3D structure. I won't spend too much time on this, but I will, what I will do is I will what I will do is I will show it to you briefly, and then I will, yeah. So this is the structure of the complex. You can see that the distance between the two hydrogens which are coordinated to, I want to label them, show labels. So that is W1, H1, and H2. It's actually, these two are not too far away, but you can see that H2 is closer than H1 in the case of this complex. So this is the complex that he characterized. It had three carbonyl ligands, sorry, and isopropyl, tris isopropyl phosphine ligands, two of them, so bis tris isopropyl phosphine. Okay, so those are the two phosphorus ligands. The phosphorus ligands are orange in color. Phosphorus is orange in color, so that's something that I will label also for you. So, and then the carbon monoxides. In the mercury program, oxygen is red and carbon is gray, so you can see them clearly. So you can see that the hydrogen positions are not they're not equidistant from the tungsten, but they are eta 2, and this was the X-ray structure that was characterized. I will send this to you. I would encourage you to see it for yourself. Now, let's go ahead. The important thing is it was reversible. This is the structure of the complex, the line diagram, and you can see that H1 and H2 were slightly different. They are not symmetrically disposed. The important thing is that the hydrogens are close enough for interaction. How did they know that? They knew it by a variety of spectroscopic techniques. Before I tell you that, in 1983, same time, independent of the paper that was published by Kubas, experimental paper was published. Hoffman and a person called Sailard. I think this is a French name, so I'm not pronouncing it right, but Sailard and Hoffman published a paper in 1983 on the theoretical possibility of H2 functioning as a ligand. What they said was a bonding molecular orbital, which is a sigma bond. The sigma bond of dihydrogen can act as a donor for the tungsten, which is now a 16 electron fragment. Without the dihydrogen, it is a 16 electron fragment. So it can donate electron density into the metal, vacant metal orbital. So this is very similar to a Werner complex, where the water molecule is donating a pair of electrons. Or for that matter, olefin, which is donating its pi bonding molecular orbital to the empty metal orbital. So this was suggested, and more interestingly, you can have pi back donation into the sigma star orbital, the sigma star orbital of H2 has got the right symmetry for accepting electron density into the just a minute, yeah, into the hydrogen. So if it does that, the hydrogen distance would be, the hydrogen distance would be weakened. Hydrogen distance would be weakened. Okay. If M2 sigma star was happening, then this would result in weakening of the HH bond, and finally it would lead to a tungsten dihydride complex. So this is on the reaction coordinate, which joins the MH2 complex to the MH dihydride complex. Okay, MH2 dihydrogen complex to the dihydride complex. So this is on the coordination or the reaction coordinate. In fact, it is now known that several of them are almost in equilibrium, including this complex. The two systems can be in equilibrium. This is a major complication because that's one of the reasons one of the ways by which the dihydrogen signal would be weakened. So you would not see the signal. Now, I will give you some more information about these interesting dihydrogen complexes. In the case of Kubas's work, there was a very sensitive balance between the size of the phosphorus ligand and the stability of the dihydrogen complex, because the dihydrogen complex was stable if the phosphorus ligand was a little small. If it was too small and if it was very electron rich, the dihydride was formed. If it was too big, then the dihydrogen complex was not stable. If it was just the right size, that is tris isopropyl, then the dihydrogen complex was isolated and characterized. So there was a very sensitive balance. So it was a little bit of chance favoring the prepared mind in this case. In this case, it was a surprised mind, not a prepared mind. Okay. Now I want you to read this paper, and this will be compulsory reading for all of you. I will tell you some brief highlights from this paper today. That's essentially my lecture this morning. About maybe 1,500 or more complexes have been characterized with dihydrogen now. So it is no longer a surprise. Okay. So between 1983 and 2010 or something, there are more than 1,500 complexes with dihydrogen. And the distance between the two hydrogens ranges all the way from 0.8 angstroms to 1.6 angstroms. That's double the size, 0.8 to 1.6 angstroms. And almost invariably, when the HH distance is greater than 1.6, the MH distance is small. When the HH distance is small, then the MH distance becomes slightly longer. So it varies from the dihydrogen complex to the dihydride complex in a fairly smooth spectrum. And it depends on the metal, the ligands around them, and of course, the solvent system could play a role, but maybe not very significant. I will tell you a little bit about the solvent system a little later. So this paper is a good summary of a lot of work, and I will briefly touch upon what is now understood for these compounds. First of all, it's very difficult to prove that a H-H bond is there. Contrary to what you might expect, the chemical shift, the proton chemical shift, NMR, 1H NMR, is very similar for dihydride and hydrogen. The main factor seems to be the large amount of electron density which is sitting around the metal and the shielding it causes. So the chemical shift is usually in the minus ppm, high field region. Okay, high field negative delta region. And if you look at X-ray, I told you X-ray is very problematic because you have a huge peak from the metal, and so the uncertainty. Look at this. The distance between the two hydrogens is 75. This is picometers, and the uncertainty is 16 picometers. So X-ray can be very frustrating. It is not very trustworthy. So neutron data, you have to go to neutron data. Neutron data suggests that it is about 84 picometers in some complexes, whereas 74 picometers is what you find in free H2. That is, hydrogen-hydrogen distance is 74 picometers, and when it is coordinated to a metal, it is elongated to 84 picometers. If you assume that the model suggested by Seilad and Hoffman is correct, this is simply the bonding electron density between the two hydrogens has been depleted, so the sigma becomes weak, and so there is a increase in the bond distance. Okay, so now how do you show that the two hydrogens are in fact bonded? Best way would be to look at the hydrogen-hydrogen coupling constant. Unfortunately, if the two hydrogens are, if they are magnetically equivalent hydrogens, then only a single resonance would be there. This is a problem with the NMR technique itself. The NMR technique will not distinguish between two magnetically equivalent hydrogens. So what do you have to do? This was in fact an experiment that was suggested by Russell Drago, the famous physical organic chemist. Some of you might have heard this name. He has written a very well-known book on physical techniques for characterizing inorganic compounds. And he suggested to Kubas that why don't you make an HD compound and measure the HD coupling constant. So if you make the HD, then you can measure the coupling constant, and that turned out to be in many complexes in the range of 33 hertz. Now 33 hertz is very close to 43 hertz, which is what is observed for free HD gas. Okay, this is the coupling constant is 43.2 hertz, and for the complex, this is HD coupling measurable in the complex is around 33 hertz. So this very clearly shows the coupling constant cannot come unless there is electronic interaction between the two nuclei. Sorry, electronic interaction which couples the two nuclei. Okay, we are talking about nuclear coupling constant. This can come about only if the electrons are communicating this coupling, the interaction between the two nuclei. So you need a covalent bond in order to observe coupling. This is something that you have to keep in mind. If a bond breaks, then you will not observe coupling. So the observance of a coupling constant very clearly shows that there is a covalent bond between the two hydrogens. Now, it's not always easy to do HD coupling measurements because you have to generate HD gas. You can generate it from by mixing hydrogen deuterium and a suitable catalyst. That is something that can be done. That is again a transition metal which catalyzes the coupling, the mixing of H2 plus D2 to give HD. Okay, so that's again a transition metal catalyzed process, and the gas can be used for meshing. So it's a probability. You will have MD2 complexes, you will have MHD complexes, you will have MH2 complexes. And the only situation where you will observe this coupling is when you have HD. Second thing to note is that deuterium has got a spin of 1, spin is a magnetic spin of 1, and so the splitting pattern that you observe for a 1 proton will be 2ni plus 1. I is the spin quantum number and n is the number of nuclei that are coupling. So if there is 1 deuterium, this is 1. So 2 into 1 plus 1, that will be a 3-line pattern. Okay, 3-line pattern is what you would observe for the proton when it is coupled directly to a deuterium. If this is observed, then what you would observe is a triplet. Okay, so this is how they determined unequivocally, which means without doubt, they determined that there is a HD bond. Now, that having been said, come back to what I told you earlier. In many crystal structures, the distance varies all the way from 74 to 130 picometers. So what happens to this coupling constant? Coupling constant should gradually decrease, right? If the interaction is less and less, it is going to decrease. So that's going to decrease. Now, there is a complication, and that complication is because something else which is connected with the proton signal, and that is the relaxation time. Now, it was proposed that because these two hydrogens are close to each other, the signal from the hydrogen is going to be improved, and in fact it is improved, because the flipping of one proton from spin up to spin down is facilitated by the other proton. So the signal that you observe for protons which are close by are in fact very good, and the relaxation rate is only 4 to 100 milliseconds. This is milliseconds, 4 to 100 milliseconds. And so here the signal's intensity is good. If there is nothing to relax the proton, then the signal intensity will go down. When hydrogen atoms are far away, then the relaxation rate becomes 150 to 400 milliseconds. Because the signal intensity varies as a function of the relaxation time, you can plot the intensity of the signal as a function of the delay time. And then you can find out what exactly is the relaxation time for the hydrogen that is being measured. So if you have a signal at minus 10 ppm, you can monitor the signal as a function of the delay time that you have in the NMR spectrometer and find out the relaxation rate. Okay, and this relaxation rate tells you whether the hydrogen is sitting like this, far away from each other, or whether they are close to each other. So there are two different ways by which you can find out. You can either do a HD measurement, or you can do what is called a relaxation time measurement to figure out whether the hydrogens are close by or far apart. So NMR turns out to be an extremely important tool. There are some caveats identified by Halpern, Halpern is Jack Halpern, the famous person who studied hydrogenation. Okay, He studied a lot of hydrogen complexes and hydrogenation reactions. So this paper that I have referred to here is in fact a paper which talks about the dihydrogen complexes and the relaxation rate utility of relaxation rate measurements in finding out the nature of these complexes. So what he said was that the ability of the hydrogen to rotate, around this axis, that is also affecting the relaxation rate. It is not just the distance. So if you remember methyl groups, CH3 methyl groups, for example, result in very good intense signals for carbon 13C resonance. Why? Because the hydrogens are flipping back and forth very fast, and they improve the relaxation rates of the carbon. A similar effect was suggested by Halpern. He said that the rotation of responsible for the relaxation rate change. So you have to consider whether it's rotating and whether it is close by. If it's rotating also, you will get good intensity. If it's close by also, you will get good intensity. Okay, so that's the complication. So finally, let me tell you about the factors which affect formation of dihydrogen complexes or hydride complexes. I have already told you that if you are able to pump in electron density into the sigma star orbital of the dihydrogen, then you will break the hydrogen and form hydrides. Okay, so let's see, by looking at this, let's see what are the factors which favor H2 complexes, which means where the two hydrogens are close by. Okay, metal is interacting with both hydrogens interacting with one another. If I have electron withdrawing ancillary ligands, that means poor donor ligands, such as carbon monoxide, particularly trans to the ligand. The ligand that we are talking about is HH. Okay, so the ligand that we are talking about is HH. So if I have a metal complex in which it is the ligand is electron withdrawing group, I should say electron withdrawing ligand, like CO, then H2 complexes are favored. If I have a positively charged metal complex, then back donation is always poor. Remember, whenever you have a positive charge on the metal is going to be more anxious to keep the electron density to itself. Now, if I have a positively charged metal, it's not going to do back donation, pushing in electron density into the pi star orbital of an olefin or a sigma star orbital of a dihydrogen is going to be poor. So if that is going to be poor, then it is better for the complex. It's better for the complex to have H2 as a ligand. So furthermore, first and second row are usually less donating electron rich, less electron rich, and early transition metals. Early transition metals, and that's not written here. Early transition metals. Then I would end up with H2. So tungsten is exactly in the right position to balance both H2 and dihydrogen, MH2 and M eta 2H2. Okay, so these are factors favoring eta 2H2 complexes. So these six metals and octahedral coordination is the ideal system to observe this MH2 complex, and that's what Kubas stumbled upon when he discovered this system, right? Okay, let me go ahead. This is directly from Kubas's more recent paper. The one that I showed you earlier is no, the one that I initially he discovered it in 1983. After that, he has published several papers, and this one is from Journal of Organometallic Chemistry, where he has expanded this discussion to formation of MH2, that is when it forms the dihydride complex and when it forms the MH2 complex. Now, it turns out that you can have heterolytic cleavage also. So when I have a very strong metal, positively charged metal system, okay, then of course, I can break it as in this fashion. Okay, I can break it in this fashion. So that's then it will become MH and H plus. Okay, this if I have a net charge of +1, then MH and H plus, right? So that's heterolytic cleavage. So if I have a very electron-rich system, then I can form MH2, that is oxidative addition to form X equals H in this case, what I'm talking about. So electron-rich systems will pump in electron density into the sigma star. That's what I have put here. This is more for electron-rich systems. Okay, and electron-poor systems will tend to do this. So either way, you can break the HH bond. So this is something that is very important for metal dihydrogen chemistry or metal hydride chemistry, where the hydrogen is now activated. What do we mean by activation? The dihydrogen is a bound system which does not react readily with an olefin. You want to activate it, you can do it either by electrophilic activation or oxidative addition. Both ways, the metal is now activating the H2 molecule to MH2 or an MH compound with an H plus, which is now going to react with the olefin or any unsaturated compound and lead to a reaction. So that's activation of dihydrogen. Exactly what I have told you just now with hydrogen can be applied to an organic molecule like methane, which is very inert. Okay, so all these arguments will come back when we talk about CH activation. So let me now talk about another way by which we can form this H2 complexes. So here is an example where I have a ruthenium complex, which is ruthenium +2. Ruthenium is a D8 system, so if it is +2, it becomes D6. So you remember, now you have 4 phosphorus ligands here around the ruthenium atom. It's exactly like your exactly like the molybdenum system, which is a D6 system with phosphorus ligands. Now you have a D8 system, which is depleted of 2 electrons through oxidative addition. Now it is reacting with Me plus OTF. Now what will this Me plus OTF do? This is a triflate ligand, right? Methyl cation with the triflate ligand. So what it does is, if the Cl is Cl minus, then it goes off as MECl. Goes off as MECl, and it forms a cationic complex with OTF as a counterion. OTF is triflate minus, this a positively charged complex. Okay. Now I've taken this from a paper. I will explain to you in the end why I've just copy pasted this paper, and the person won't mind me doing this. So this is the reaction that happens. Now I want to tell you something about it. Now this is a hydride complex, right? Now this is a hydride complex. This hydride complex interacts with a variety of ligands. This is again 2+ now, ruthenium 2+. So it can accept this acetonitrile transposition and form a stable complex. This was characterized. So this is one way in which you can you see the reactivity of the hydride complex here. Now it turned out that if you took this complex and treated it with a strong acid, HBF4. HBF4 is a strong acid. Now you can protonate this complex. This is protonation of this complex, and the proton in fact reacts with this hydrogen. What color it is in? Let's make it red. So this is it interacts with this hydrogen. This H+ interacts with this hydrogen, forms an H2 complex. Okay. So for a variety of phosphorus ligands, these are all variations in phosphorus, so we don't have to worry about it. Argue with 4 phosphorus ligands. If they treated it with HBF4, that just protonates this, and you now form a dihydrogen complex. This dihydrogen complex was characterized by crystallography, and it was characterized by NMR techniques, whatever I have told you, relaxation rates, HD measurements, HD coupling constant measurements. It was done in this study. So this is a complex that was isolated and characterized. You can see the dihydrogen now. This is the dihydrogen interacting with the ruthenium with the chloride. This was characterized as a stable complex. This is again now a D6 system, right? So it has no problems in forming this. This was in fact done by Professor Jagirdar in our department. So that's why I just copy pasted from the paper. So these are complexes which they characterized, I think, sometime late in the 90s. They also looked at other dihydrogen complexes. Interestingly, you could protonate these hydride complexes with H+, and you would end up with hydride dihydrogen complexes. Okay, so I want to show you just before I end, I want to show you some of these hydride dihydrogen complexes in 3D. I will post all of these files. I want you to go through them for yourself because that's the best way to learn. Okay, so I want you to manipulate the structures and understand how the dihydrogen is in fact interacting with the metal. Okay, what's the hydrogen-hydrogen distance? What happens when you have different ligands, and so on and so forth. Okay, so this is the study that this is from the same paper that I have taken. I will show you the 3-dimensional structures for a minute. The structures that that were studied. This is, you can see that it is very crowded, but unfortunately I can't turn off the hydrogens because you have, I want to show you the way in which the ruthenium, this is the ruthenium is bound to the dihydrogen. This is a structure characterized by Professor Jagirdar and so okay, so I don't know whether I can really hide the hydrogens here selectively. If I say that hide the hydrogens, then everything is hidden. So I have to show them. So I hope you will be able to see it. This is drawn as if there is no hydrogen-hydrogen bond, because what happens is in the crystallographic program, automatically it calculates the distance, the covalent bond distance, and if it's more than the covalent bond distance, that is 0.74 angstroms, then the distance is not marked as a bound species. So let me measure distance, and then this is now 1.069. So that is 106 picometers. Okay, 106 picometers. It's way above 74 picometers. So this is still not very close. As I told you, dihydrogens start after 1.6 angstroms. So this is still a dihydrogen complex. It is still classified as a dihydrogen complex. Some more systems. One thing that I have not mentioned, which I wanted to mention, was the fact that hydride ligands can bridge. Here is an example where the hydrogens are shown as hydrides, two hydrides. This is now a tungsten species. Okay, this is a tungsten species. What they have done is they have reduced the steric congestion around the phosphorus. They have put two methyl groups and one phenyl group. And the moment, because you have put two methyl groups, this phosphorus becomes more electron donating. The phosphorus becomes more electron donating, then the distance between the two hydrogens is, the distance between the two hydrogens is now 1.7, well, sorry, 1.7 angstroms. I hope you are able to see it now. Okay, 1.716 angstroms. You've made the phosphorus less sterically demanding. At the same time, it's more electron donating, and so the hydrogen-hydrogen distance becomes larger. Notice also that this complex is in fact 8 coordinate. 4 phosphorus ligands, 2 chlorines, and 2 hydrogens. Okay, so this is the another complex that I wanted to show you. I will also show you one other system. This is a system where tungsten atoms are being bridged by 2 hydrogens. Tungsten is being bridged by 2 hydrogens. So hydrides are good bridging ligands, and they are at the same time, just like chlorides, they are capable of bridging. And then let me show you just one more system, and that is I think, this is the last one. So in many systems, the hydrogen, there are so many hydrogens around the metal that they can interconvert. So here is a ruthenium. Okay, ruthenium, 2 phosphorus ligands. Okay, 2 phosphorus ligands, and and actually 1 nitrogen ligand. And look at this interaction. 2 hydrogens are close by. It could be, let's measure the distance now and see what it is, but my suspicion is that it's a dihydrogen hydride complex. So this is 1.00 angstrom, so that's a dihydrogen. But these 2 hydrogens are slightly further apart. This is 1.62 angstroms. Okay. So but this will interconvert. So in other words, this will become short and this will become long. So fluxional behavior is very common in these systems. So I'll have to stop here because of the time. Let me stop and ask if you have any questions. Otherwise, I will stop recording, and if there are no questions. Now, the test will,
Sir.
one second, Arko, before you continue. The test will be on 2nd December. Okay, test will be on 2nd December. I sent a questionnaire and a mail to some of you who have finished answering the questionnaire. So if you have a problem, you please mention. Otherwise, test will be on Monday. That is 2nd December. Okay, Arko.
Sir, how are D6 metal complexes favoring the eta 2 hydrogen complexes? Is it due to the electron count?
I told you there are so many factors which are involved. Electron count is one of them. Electron count, electron density around the metal, steric phenomena. So that's why chemistry is a lot more complicated and a lot more interesting.
Okay.
Yeah. So I can't pinpoint and say. If you compare a series of closely related complexes, you can very clearly see there are two effects. One is electron density, another is electron count. Okay, electron density and ability to pump in electron density into the sigma star orbital.
Okay.
Yeah.
Hello, sir.
Yeah, who's this?
Sir, this is Sushan, sir.
Yes.
Sir, what are the orbital involved when the hydrides acting as a bridging ligands? Actually,
yeah, it's a it will be a 3-center 2-electron bond. Okay, so it's a 3-center 2-electron bond. We can draw the orbitals fairly easily. There are 2 empty orbitals from the metal and 1 filled H minus, which has got 2 electrons. Okay, so that's the bonding system. 3-center 2 electrons.
okay, sir.
This is Pankaj. You mentioned that the back donation from metal to hydrogen pi sigma star system. So
Yeah.
how the symmetry is matching there? Can you just elaborate briefly?
Yeah. So if you remember, you have, I have these orbitals in fact drawn. I will post them, but because it will take me some time to open it up, I'm going to just quickly draw it. So if you remember your coordination geometry, this is an octahedral complex, right? So your filled orbitals are your dxy in this case. Okay, this is going to be your dxy orbital. This is your metal. Those are the orbitals, right? So this is your sigma star. This is your sigma star. So it's got the right symmetry for interacting with the sigma star. This is filled orbital on the metal. So I will post for you MCO5 orbitals, and you will see that exactly it is not as traditionally shaped the way I'm drawing it, but the shape of these orbitals are right and the right shape for interacting with the sigma and the sigma star. So the sigma orbital will be the one which is dx squared minus y squared, mixed with, of course, other. So this is the empty orbital, and the hydrogen is lying in this, right? So this is the filled orbital in this case.
Thank you.
Yeah. Any other question? Okay. So otherwise we stop here and meet on Friday. And on Friday we will talk about acetylenes and dienes. Let me see how much I can cover with acetylenes and dienes on Friday. I might post a lecture earlier if I manage to record some slides. I see no other questions, so we'll stop here. You can all leave and I will stop recording.